All right, pre-calculus. We are moving into our next unit where we are going to talk about algebraic fractions. And today we are going to specifically talk about not necessarily an algebraic fraction, but a type of fraction, irrational numbers themselves are not a type of fraction, but we will define rational numbers and utilize that idea, which are fractions. So we will be using the idea of fractions to do some proofs today. So a rational number, we define that as a real number R represented by the letter R is rational if and only if there are integers A and B where B is not equal to 0 such that R is equal to A over B. The big defining factor of if it's a rational number or not is, can it be written as a fraction? Irrational numbers then are any number that cannot be written as a fraction. For example, pi is irrational, and then the irrationality of the square root of 2, which we are going to prove down here, is just that the square root of 2 is irrational. We'll prove it below. Now, before I get into the proof, part of the proof for this is going to involve knowing what the general form of all even numbers looks like and the general form of all odd numbers. Now, I didn't learn these until I was in college, but they're not hard to understand. Any even number can simply be written as 2 times some other number. So we just use the letter K to represent that. And then any odd number can be written as any even number plus 1. Okay. So for our proof, the thing we are trying to prove here is that the square root of 2, and I'm going to define that as s. So the square root of 2 is irrational. Now, that's kind of on its own as a direct proof, kind of hard to do. So as an indirect proof, we're going to try to seek a contradiction where we're going to assume the opposite of this. And if we show that the opposite of this can't happen, then this has to be able to happen. So I'm going to start my proof by simply just stating seeking a contradiction. We're going to suppose, or we can say assume, not s is true, meaning that the square root of 2 is rational. In lowest terms. We haven't really talked about what that means. It just means that it's reduced as far as it can be. There is no common factor in the numerator and denominator of the fraction. So we say if the square root of 2 is rational, then the square root of 2 has to equal some fraction a over b. Again, in lowest terms. There's no common factor that we can divide out of a and b. So, by squaring both sides, I'm going to get 2 is equal to a squared over b squared. I'm going to write by squaring both sides. I'm just getting rid of the square roots. And then I don't want any fractions in what I'm trying to prove right now. I want to move things around. So I want to show that there is no common factor between these two. So I'm going to multiply both sides by b squared. So I can say 2b squared is equal to a squared by multiplying by b squared. Now, by definition, what we have here, in fact, I'm going to say by definition of evenness, which I'm not sure if that's 100% spelled correctly with two N's. You could also just say by definition of being even. A squared is even because a squared is now written as 2 times something. So it doesn't matter what b is. 2 times something is going to give us an even number. We can also then imply, so a is also even. Because if we square to get an even number when we square something, we have to square an even number. If we think about it, 3 squared, 3 times 3, an odd times an odd, is going to give us 9, which is another odd number. If I take an even number times itself, I will get an even number. But an odd number times itself will always give us an odd. So then, I'm going to take 2b squared, and I'm going to replace a with 2k. Because we know a is even, so 2k squared. Or we could write it as 2b squared is equal to, if I actually square 2k squared, I'd get 4k squared. And I'm going to isolate b, so I could also say, or b squared is equal to 2k squared. So from here, we can actually use the same argument we just used, but replacing the a's with b's. So by definition, then I'm not going to use evenness. I'm just going to write even. B squared is even. So b is even. Now what we've shown so far is that both a and b, so a and b, are both even and must have a common factor of 2, because any even number is always divisible by 2. So this contradicts our assumption that a over b is in lowest terms. So the square root of 2 cannot be rational So the square root of 2 must be irrational. And that's the end of our proof. We just had to show that the square root of 2 is irrational. And that's exactly what we did. So let's just go through it one more time. Our goal was to show the square root of 2 is irrational. We did this by finding a contradiction, assuming that the square root of 2 is rational in lowest terms, meaning as a fraction, we can't reduce it anymore. So if it is rational, it can be written as a fraction of a over b. So if I squared both sides, that's what we did. A over b squared is just a squared over b squared. This is still valid math. I can move b to the other side through multiplication. Haven't changed the problem yet. From what I introduced you to, the general form of an even number, a squared has to be even. And in order for a number to be squared and even, that means that number itself is even. So I then just substituted 2k, the general form of an even number, in for a, found some equivalent statements to isolate b squared. And again, by definition, b squared is now equal to 2 times some value, so b squared is even. And just like with the a, if b squared is even, that means b has to be even. If both a and b are even, that means they're either the same and they're divisible by each other, or at a minimum, they are two different even numbers that have to at least be divisible by 2. So because of that, a over b was not in lowest terms, or can't ever be in lowest terms. So this contradicts the assumption. And then since the square root of 2 can't be rational because of that, it has to be the opposite, which would be irrational. We are almost done with this lesson. I have a little theorem, and we're going to do a little one more proof together. So our theorem first is if n to the power of 2 is divisible by a prime number, p, comma, then n is divisible by p as well. If we think about it, 20, no, let me think of a different one. 16 is 4 squared. So let's pretend n is 4. 2 is a prime number that we can divide 16 by. 4 is also divisible by 2. That's really what this statement is saying. So what we are going to prove in this next example is that the product of a rational number that is not 0 and an irrational number is going to result in giving us an irrational number. Now, what I want to start off by doing is I want to rephrase this using some variables. So I'm going to actually start by saying let P be what needs to be proved. I'm just taking a variable, assigning it as P. So P is going to be the statement if R is any non-zero rational number and X, and you could use any variables you want for this. I'm just using P, R, and X. X is any irrational number comma, then R times X is irrational. This is just restating the sentence they gave us. Now, I am also going to say we're going to let the variable s equal r times x. I'm going to do this as an indirect proof. So I'm going to do this by contradiction again. I think a direct proof is going to be a little difficult. If I can show that r times x it can't be rational, then it has to be irrational. So I'm going to start this next line by saying seeking a contradiction assume s is rational. So r times x is rational. Since s is equal to r times x, if we isolate x, we're just isolating the irrational number, then x is equal to s over r. Since r can't equal 0, this will give us a real number at least. Now the quotient of two rational numbers is itself rational. So x has to be rational. But wait, we earlier said that x is irrational. So we can say this contradicts what we defined x to be. So s is not rational. Therefore, p has to be true. Meaning that if we multiply an irrational number like the square root of 2 by a rational number like 1/2, we're going to get an irrational number back. We will not get a number that can be written as a fraction with just in simplest terms. There is one last vocabulary term here, and it's the conjugate of irrational numbers. So we can say the irrational numbers a plus the square root of b and a minus the square root of b are conjugates of each other. Just remember, if we were to have one of a number in this form, in the denominator of a fraction, to rationalize it, we have to multiply by its conjugate. And that's going to wrap up this lesson.